Okay, so you should be thinking, where does this value, the Planck constant h, come from? So there's a very simple experiment we can do to get a value of the Planck constant. You may have to do this as a core practical as part of your A-level, but even if you don't need to do this, it's a useful thing to consider. So what we have is a straightforward circuit here. We've got a variable power supply. In this diagram, I have a fixed power supply connected to a variable resistor, which allows me to vary the output. And I've got a voltmeter attached across an LED. So you should be familiar with these symbols from the electricity topic. So the way that an LED works, you might remember, is it will only work when it reaches a certain voltage, typically 0.6 volts. And at that point, electrons can flow. So the resistance, which was previously very, very high, it now behaves in a more linear way. So we're going to consider a single electron passing through the LED. As it does that, the electrical energy it had before is all transferred into the energy of a photon of light. So the relationship is quite straightforward. The energy lost by the electron as it passes through the LED is equal to the energy of the photon emitted. Now, you should remember from the electricity topic that the definition of voltage is energy per unit charge. So we can make energy or work done the subject. So W or E is equal to Q times V. So the energy lost by the electron is equal to the charge multiplied by the voltage. And that in turn is equal to the energy the photon emitted, as we know is HF. So we know the electron charge is the elementary charge, 1.6 10 to the minus 19 coulombs. And we can measure the voltage with our voltmeter. So we need to start off on 0 and increase the voltage until the light is just being emitted by the LED. At that point, we can measure the voltage using the voltmeter. So by multiplying the charge on one electron and the voltage across the LED, we can calculate the energy of the photon. So we can do this for a range of different colors of LED. So we know the frequency of the light already. That will be given as part, so that information is part of the LED. So we can work our way through the LEDs. So red, orange, yellow, green, and blue. Each one will have a different voltage associated with it, therefore a different energy of photon. And as expected, because E is equal to HF, then we get a proportional relationship, a straight line through the origin. So C should be equal to 0. E is plotted on the y-axis. F is plotted on the x-axis. Therefore, if you work out the gradient of this line, that will give you the value of H, which is Planck constant. So you might get asked to explain this in the exam. This could be a longer response question. But even if it's not on your specification, I think it's a really useful thing to be aware of. The final thing we're going to consider in this video is this idea of the electron volt. So we've seen already that the energy involved when we're calculating photon energy is very, very small, 10 to the minus 15, 10 to the minus 16 joules. So that's not a very convenient unit of energy. So more convenient is something called the electron volt, EV. Now, if you compare this to what you might have studied in mechanics, you might have done this at GCSE, you had to learn about the kilowatt hour. And that was more useful when we're talking about very large amounts of energy, for example, in domestic energy bills. So we could talk about units of electricity use, so 15 units or 100 units, and that's the kilowatt hour. So this is the same idea, but for very, very small values of energy. And the definition is as shown. So if I have an electron moving through a potential difference of 1 volt, so it could either be accelerated from 0 speed up to a maximum, or it could be going the other direction, slowing down. So whichever way, the energy associated with that, if we have 1 electron and 1 volt, then that's 1 electron volt. And we can actually calculate that because we know W is equal to Q times V, as we saw on the previous screen. So the Q is the charge on 1 electron, 1.6 10 to the minus 19. So if you multiply that by the voltage, which is 1, you get exactly the same value. So basically the electron volt, this measurement of energy, is the same number as the charge on an electron. But rather than coulombs, we're now referring to this as joules. This is a type of energy, or a unit of energy. So you might get values in joules, and you have to convert them to EV, in which case you need to divide by this number, 1.6 10 to the minus 19. If you're going the other way, if you have EV and you need to convert to joules, then you need to multiply by 1.6 10 to the minus 19. Right, a few worked examples. So if you want to pause the video and have a go at these, you can do, but they're fairly straightforward. So this first one we've done already. This actually defines, as we know, the electron volt. So if we're saying it's the energy associated with 1 electron and 1 volt, E is equal to V times Q. So 1 volt multiplied by the elementary charge, which we know, we get the same value. So this is our electron volt, 1.6 10 to the minus 19. And if we're going to convert, so if I have 2.9 EV, then I need to multiply by 1.6 10 to the minus 19. So as expected, 2.9 electron volts in joules is a very, very small value. If we're going the other way, if I have this very small value shown here, 7.3 10 to the minus 19, if I divide by 1.6 10 to the minus 19, then I get a more workable number. So it should tie in with this idea of convenience. So if we're talking about so many EV, in joules it's a very small value, and conversely, if we have a very small value in joules, in EV it should be typically 2 or 0.5 or 50 or something like that.